So today I'm basically going to be telling you, so I work in the algebra research group here, which is part of the maths faculty, and more specifically I work in representation theory. But I thought I would just explain to you some fun sort of Braid group facts so you get a little bit of a taste of what doing algebra research is like. So maybe to start off with, I can just get a show of hands of like, I don't actually know anyone here, almost. So who here is in like first year? Anyone? Few people? Second year? And like third year plus? The rest, I guess. Yeah, awesome. So I think in that case, I need to start off by telling you what exactly is a group before I tell you what a braid group is. Right, so a group is a kind of thing that we study in algebra. And a group is going to be a set of things, which you normally call G for group. And I want this set to have a multiplication rule that takes two things in my set and gives me another thing in my set. And I also want it to have an inversion rule, which takes a thing in my set and gives me another thing in my set. And I want these rules to satisfy some axioms, which I'm not going to write down, but I can give you some examples. So, first, does anyone know any examples of groups? Go.
Cyclic groups.
Cyclic groups. Yeah, so cyclic groups are sometimes written Z on NZ. But you also might know them as the roots of unity, right? So if I take like e to the 2 pi I on n, 2 pi I k on n, for all integers k, in the complex, these are all complex numbers, and I can multiply them together using normal complex number multiplication, and I get another thing. And I can also take inverses, right? The inverse of one of these is the same as its conjugate. Any other examples?
Integers over addition.
Yep. So I can take the set of integers, and for my multiplication rule, I can take addition. Right, so that's the thing that gives me something new in the group. And inversion in this case is going to be subtraction, or like minus sign, right? Because if I take n and minus n and I add them up, I get back to 0. So that's kind of like the inversion. So a non-example of a group is the integers with multiplication. And the reason is, like, the multiplication is just fine, but you can't invert things. Because like once I have a 2, there's no integer I can multiply 2 by to get back to 1. Yeah? So groups are algebraic structures where you can multiply, but you can also divide, basically. You can always get back to some kind of 1. So a very important class of groups are called symmetric groups. So a symmetric group so they're called Sn, and I'm going to take all of the functions that mix up the numbers 1 to n, basically, such that f is bijective. Right, so this means that f is an invertible function. So automatically I know that I have an inverse, and my multiplication here is going to be composition of functions. So for example, I could take f is, I'm going to write this in kind of a funny way, which will be obvious later on. So I could take 1 maps to 2, 2 maps to 4, 3 maps to 1, and 4 maps to 3. And I can take another function, which has to be a bijection, 1, 3, 2, 1. And then I can do f composed g, right? Which is literally I just do g and then I do f, right? So 1 goes to 1 and then 1 goes to 2. So over here I get a 1 goes to 2, and so on. 2 goes to 3, 3 goes to 1. Sorry, 1. And I think this is what I get for the rest of them. So the symmetric group is kind of like the canonical example of a finite group. So this group here is a finite group, this group here is a finite group, whereas this one here is an infinite group. This one is not a group. And there's a theorem which is actually not very deep at all, which is that any finite group is a subgroup of one of these. Right, so I can select some permutations that represent any group that I want, as long as it's finite. So if I have a cyclic group like this, I could just take a permutation which is a cycle, right? 1 goes to 2, 2 goes to 3, 3 goes to 4. And then when I power that cycle up, I get sort of like a multiplication table that looks the same as this. If I restrict myself to those kind of permutations, that's the same thing. So what's nice about these is that, see, this looks very algebraic, but how can we make the study of permutations a bit more fun? We could write them as diagrams. Right, so these are sometimes called wiring diagrams or something, and I'm going to read my diagrams from the bottom of the page towards the top of the page. Right, so 1 goes to 2, 2 goes to 4, 3 goes to 1, and 4 goes to 3. So there's my F. Here's my G. So 1 goes to 1, 2 to 3, 3 to 2, 1 to 4. Right? And then how do I make F compose G? Right? I literally join up the diagrams in the middle. So this is like stacking 2 diagrams on top of each other. So I put the diagram for F and I paste it on top of the diagram for G. And what do I get? You can kind of see that I get these funny loops in the middle. And you can kind of, figure out the rules that you should be able to do. So I get these 2 things crossing over and I can sort of pull them apart. So I get something like this. Right, which is the same as this guy over here. Right, so, why do I care about writing stuff like this? There's some laws of groups that you need to make sure are satisfied. So what is this thing called associativity, which you've probably seen for matrices? I really want that when I multiply A by B, and then I multiply that by C, this is the same as doing this. And this is not always easy to see, but if multiplying stuff is just pasting it on top of each other as diagrams, then this is kind of very easy to check. And so there are whole parts of algebra about making what do you call it? Diagrammatic algebras. So you can go and sort of experiment around with what are the kind of rules that we want. What kind of rules can I use to simplify a diagram? So one of them might be, so anytime I see something like this, I'm allowed to just pull these through. Right, so all of my sort of loops like that cancel out. And another, so what is this saying, by the way? So let's get a tiny bit technical. I can introduce some special elements. So this is going to be S1, S2, and S3. Right, so this is the permutation that switches 1 and 2. This is the permutation that switches 2 and 3, and this switches 3 and 4. And these satisfy something called the Coaxial relation. So if I do this, then this should be the same as doing this. Yeah, you can kind of see I've just sort of moved this wire at the back, to the other side. So this is called a Coaxial relation. And if you've ever looked at knot theory, this is also sometimes called the Reidemeister 2 move. But we'll get to that in a sec. So it turns out that these are all you need to generate the symmetric group. And these are all the relations you need to specify. So this relation, when you read it, what's this diagram? This is an S1 stacked on top of an S1. So this is saying S1 squared is the identity permutation. what's this one? This one is saying S1, S2, S1 equals S2, S1, S2. And then I have one other relation. I've used this board space in the grades way. I have one other relation that basically says that if I have crossings that are far apart, then I can just move them past each other. Oh no, that's the same thing. Alright, so what's this one saying? S1, S3 equals S3, S1. Yeah, and S4, S1 would also equal S1, S4, and so on. So it turns out these are all you need to describe the symmetric group. And the nice thing is that these relations kind of come from the diagrams, right? You can take these relations and come up with these diagrams, or you can sort of come up with these diagrams first and like extract the relations from them. And that's kind of the direction that we care about in diagrammatic algebra. You might be able to, you can imagine there's some, crazy expression in the S's that might be, much more easily checked as a diagram or something. Right, so what is a braid group? Can anyone guess what a braid group is already? Yeah.
I'm going to assume it has something to do with 3 strands linking up with each other in like a way where you can separate them out.
That's a good guess. That's close. Yeah.
Is it related to this, but something to do with like recording the history of the operations?
Yeah, that's right. So in this symmetric group, I don't really know whether this crossing goes sort of over or under this crossing. I don't care, because permutations don't remember that. But braids do. So that's like the one change that we're going to make. So in a braid diagram, I've got a particularly interesting braid that I can draw here. Things are allowed to go under and over each other. So I might have something like that. These go up here. And then maybe this one goes under everything over to here. So this is an example of a braid. So let's call it beta. And this is a member of the braid group on 4 strands, right? In the same way that this is a member of the symmetric group on 4 letters. And how to think about braids is, literally you think you have sort of like a bar up here and a bar up here, and there's some ropes tied to each part of the bar, and the ropes are going under and over each other. And for technical reasons, I normally don't want to allow a braid to turn around and go up. It doesn't really matter. I kind of want braids to never get horizontal, but that doesn't matter so much. So I still have, I can write down braids. Great. And yeah, what was your name, sorry?
No, Jack.
Jack? Yeah, as to Jack's comment, I could also write down like a plait. So if you're plaiting hair or something, what do? You put this one over, then you bring this one over, then you put the right one over again, then you put this one over, etc. So you could extend this plait as much as you wanted. So the first thing to notice about the braid group is that it's infinite. So the symmetric group is finite. There are only so many permutations you can do once you choose a certain n, whereas the braid group is infinite. And an easy way to see that is that the braid group on 2 strands, what do I have here? Maybe something like this. You can see that maybe I call this over, what's this, over again, under. I really just have to count the number of overs, subtract the number of unders, and then that tells me what kind of braid it is. Yeah, like you can see here that this under and this over cancel each other out, because I can just push this past here. So I can make braids. Multiplication is the same. I stack diagrams. Does anyone know how to take the inverse of a braid?
Sounds painful.
Hey?
Sounds painful.
Sounds painful. It's a little bit painful to draw, but it's not actually very painful to describe. So let's take a random braid. And maybe this one links once more around here. Any more guesses? Yeah.
Just so like down the bottom you've got something you've got like crossing and just like undo that one so it make it
Yeah, like undo
blank,
this one
yeah,
the
and
other way
then
around.
Go one at a time.
Yeah, and go one at a time. So a very compact way of saying that is if this is my braid beta, I just have to write it upside down. Now, I'm gonna try to do this right. So difficult. I think I've done that wrong. I think there's like one extra crossing here that is not meant to be there. Maybe? You get the idea. So this is kind of nice. This also works in the symmetric group, by the way. If you just think about, how do you read a permutation back to front? It's just basically just flipping the diagram upside down. So these are braids, but because we're algebraists, we would like to talk about braids a little bit more algebraically. And it turns out that we can do something really similar to in the symmetric group over there. So I can introduce a couple of special braids. So I have my sigma 1, which will be the left hand goes over, sigma 2, which is the next one goes over, sigma 3 is the last one goes over. So the tricky difference about these is that sigma 1 and sigma 1 inverse are no longer the same thing. Right, so in sigma 1 inverse, the other one goes over the top. Whereas in the symmetric group, this relation here is the same as saying that S1 is its own inverse. Yeah, S1 inverse equals itself. This is not true in the braid group, and this is essentially where a lot of the complexity comes from. But then you can figure out, what relations do hold. So I don't have sigma I squared equals 1. That doesn't work anymore. But what do I have? So this one down here has to work for braids as well, right? Because if I have two braids that are moving far apart, I can just sort of move the crossings past each other. So I do have stuff like sigma 3, sigma 1 equals. Right, this is this. So this kind of relation still works. And in fact, the Coaxial relation still works. So let me draw it a little bit bigger. So this is sigma 1, sigma 2, sigma 1. And this is going to be equal to this one here. right? And you can see that this sort of red strand running through here is kind of just moving under everything. Yeah, and then this other strand is moving over the top. And now this is really actually the Reiter-Meister 2 move from knot theory. We'll get to that in a sec, but just in case you've seen that sort of thing before. So the upshot of all of this is that you can present the braid group as a group generated by n-1 generators, right? Because I switch each strand, and I want sigma I, sigma j equal to sigma j, sigma I, if I and j are far enough apart. And otherwise I have this triple relation. And if you wanted the symmetric group, all you would add here is sigma I squared equals 1. That would give you the symmetric group. So if you haven't seen this before, this is kind of a compact way of writing down a group. I want to take all of these symbols and all of their inverses, and I'm allowed products of any of those, and then these are the simplification rules that I'm allowed to use. That generates a group. It's not generally a great way to describe a group, but it's a very concrete way to describe a group. So a lot of my research involves computers, and I like to do stuff with braids in computers. So, you know, how do you do that? This is a diagram. This diagram is very annoying to represent in a computer. Right? If you just try to think about like what kind of data structure you would use to store a diagram, it gets messy very fast. Something like this, where I represent words just basically like, you know, I've got a braid. What braid is it? It's sigma 1, sigma 2 inverse, sigma 3, sigma 1 inverse, sigma 2 inverse, sigma 1 or something. That seems a bit more computable. But now you have a different problem, which is that you might want to tell whether two of these are equal. And it's not clear how to apply these simplification rules to tell whether these are equal. So, to give a concrete example, so in S6, I have S4, S3, S2, S5, S4, S3, S2, and this is equal to S5, S4, S5, S3, S4, S2, S3. And the question is, can you write a computer program that mechanically checks whether these two things are in fact equal? You know, it has to sort of apply these relations in every single possible way to try to move between them. And this is something that is ridiculously inefficient. And actually, a little bit more interestingly, these kind of things are called group presentations. And you can't actually write a computer program that will take in an arbitrary group presentation, two elements written like this, and tell you whether they're equal. That's called an undecidable problem. And it's equivalent to the halting problem, if you know that from computer science. But basically, there are some algorithms that can't be written, and this is one of them. However, if we specialize just to certain groups, like just the symmetric group or just the braid group, then we can. So, does anyone have any questions so far? Please interrupt me if ever you have questions.
So a braid group is decidable?
Yes.
Okay.
Yeah.
But in general?
Usually specific groups are decidable. But yeah, you can't make one that is general, that decides everything.
But all finite groups should be decidable, right?
Yes, all finite groups are decidable for silly reasons. Yeah. You might not actually want to write down the program, but yeah, all finite groups are decidable because you could write down the whole multiplication table and then just do it.
Oh, yeah.
Like, yeah. So technically decidable, but like you wouldn't want to do that for a symmetric group, right? Because you know, how many permutations are there on 60 elements? Yeah, it's quite short to write down a permutation on 60 elements, right? I'll just give you 60 numbers, but there are 60 factorial of these, which is like, I don't know, it's like 10 to the 80 or something, like some ridiculous number.
It's like saying you can reverse all the hashes if you just have the hash table for
Yeah,
every
exactly. So if you want to write down the multiplication table for this, you're already up to like 10 to the 2 times 80 things. So that's not good. So, you know, in practice, you actually need efficient algorithms even for finite groups. But yes, for like the sort of pure philosophical, is it decidable? Yes, all finite groups are decidable. So what kind of techniques can you use to decide these things in braid groups? So there's something called the Garside normal form, which I won't define properly, but I'll give you a hint of what it looks like. First, I can tell you about a fun, interesting braid. So there is a special braid called the full twist. And I can describe it to you with my hand a bit better. The full twist is when you go like this. Whoop. So in diagrams, it looks like this. Yeah, so if you imagine your hand, whoop. Oh no, this is the half twist, sorry. So the full twist would be 2 of these. Yeah, so the full twist is you start here and you end up like there. So the half twist is quite an interesting braid because you can sort of factor anything off this that you want. So any simple crossing can be factored off the bottom of this. So for example, I want to write this half twist with this simple crossing at the bottom. How can I do that? Well, you can see that there's this simple crossing up here. And in this case, all I sort of have to do is push this down to here. So this is equal to so I move this crossing down to here, and then I do the rest of the thing. Yeah, so I push this down to here, and now, for convenience, I can write this a little bit lower down. Right, and so you can see that here I have delta, but I've written it as a product of 2 things. One of them is my sigma 3 that I wanted to bring on the bottom. And then there's something else, which, you know, needs to be delta sigma 3 inverse. But the point is that everything here is a positive lift of a permutation. So this is something I haven't said before, but you know, if you take a permutation diagram and you ask, you know, how do I turn it into a braid diagram? You know, it's basically the question of like, how do you resolve each crossing? Does each crossing go over or under? So if I resolve each crossing so that it looks like one of my generators, so from reading from the bottom of the top, the left thing goes over, then I have what's called a positive lift. You could define a negative lift, but you know, let's just stick with positive lifts. And so I've written this whole thing as, you know, delta is a positive lift of a permutation, and I managed it to factor into sigma 3 and delta times sigma 3 inverse. Let's call this thing sigma 3 star. Right, that's this braid diagram on the top here. So what do I have now? I have an equation. So delta is sigma 3 star, sigma 3. And so if you rearrange this, you get an expression for sigma 3 inverse. Which side does this go on? This side. So I've managed to write something with an inverse as a product of a positive lift and the power of delta. And I'm going to allow myself negative powers of delta, but that's the only negative powers anywhere that I'm going to allow myself. And this kind of shows that, it's at least possible to write some inverses this way. And in fact, it's possible to write everything in the braid group this way. So all braids are written uniquely as delta to some power followed by a bunch of lifts for delta any power and W1, WK permutations with WI, the positive lift. So there are a couple of conditions on these W1s and WKs. So adjacent things, I've sort of got to push as many segments to the left as I possibly can. When I stick two braids on top of each other that are positive lifts, I might be able to keep moving braids to the bottom one and keep the thing still a positive lift. And then eventually the bottom one fills up and essentially becomes delta. This is the positive lift of the reversing permutation, which is kind of like the biggest permutation. And then that delta can fly to the front. So, this is, I won't go into this anymore, but this is a little bit of interesting combinatorics about the braid group. And this is how, like in the programs that I write, I deal with it. So it's very easy to write programs that deal with permutations. And it's relatively easy to figure out the compatibility of permutations. How do you snap two of these words together? What do you do with that? And this essentially means that I can take something like this and write it like this. And this uniquely means that it's a normal form, right? So if I have two different words here that I don't know if they're equal or not, I write them in this way, and if they end up being exactly the same thing, then I know the braids are equal. So that's kind of like a nice way of dealing with braids. Right, so I was going to say a little bit about representations, but maybe I'll skip that for now and just tell you, why do we care about braids? So you should always ask yourself this when you're doing mathematics, like, cool, this is an interesting object, but ultimately, like, why do I care about it? And so in algebra, there are lots and lots of interesting objects, but algebra is, in some sense, an easier topic to approach because it has so much structure. Right, so like an example is braids always have inverses. Braids have this nice structure here. I can multiply braids, things like that. So problems that don't have very nice structure are often the harder ones that we actually want to solve. And we try to approach them using algebra. And at some point we get lost along the way and start just studying algebra for the sake of algebra. Because it's nice. But we should always keep in mind of the the problems that these things were actually developed to approach. So who has heard about knot theory? Almost everyone. So in knot theory, people are obsessed with this thing called the unknot. Unknot, which is not a knot. It is a knot. And then there are sort of other, it's always dangerous drawing these things in talk. So this is the trefoil knot. So in knot theory, you imagine that you have a piece of string, and the string is tied at both ends, so there's not loose ends, it's tied together. And you ask yourself if there's some way of rearranging that string so that it just becomes a circle. And sometimes there's not. If I've drawn this correctly, there is not a way of sort of untangling this string from itself and turning it back into a circle. Right, so this is called a knot. And if you want a formalism, a knot is a continuous map. So it's a continuous injective map from S1, which is the circle, into R cubed. Right, and then when I draw diagrams like this, you imagine that this knot here is actually living in space, and I'm just looking at it from some perspective. So there are these moves that you can use. So I guess the hard part about knot theory is that you can draw a whole bunch of stuff that is complicated, but this is still the unknot. Right, and then you can draw a whole bunch of other things. And ask whether they're the unknot. And that's now a very hard problem. And so there are, knot theory sort of lands in the realm of like topology and things like that. But algebra is one way that you can use to study knots. So, this is clearly the unknot. This is unclearly the unknot. This is the trefoil knot, but you might have to make some kind of argument as to why you can't unknot it. Who knows what this thing is? Probably the unknot. It is? Yeah.
I think so.
This is kind of the rule of giving a talk, where like anytime you try to draw a non-trivial knot, you end up drawing a trivial knot, and the other way around too. Also related to knot theory is links. So a link is just a bunch of knots, but the links might be, kind of linked together like this. So this is the hop link. Very fancy name for something that's basically just two rings joined up. And I'll draw the Borromean rings at the end. But if you've seen the Borromean rings, you can sort of make like 3 bracelets that are sort of together, and if you remove any one bracelet, the other 2 will fall apart. So that's an interesting example of a link. So braids are connected to knots, which you can maybe already see from the diagrams. But how do you make that explicit? So if I take, let's take a simple braid. This is my braid, beta. Then what I can do is I can form the closure of beta, which means I draw it again. And the closure just means you loop it back to itself, like this. So maybe we call this cl beta or something. And this is now a knot. Or rather, it's going to be a link in general. Right, because some braids, if I take a trivial braid and I form its closure, then I have a link. Just because it doesn't have one component, it has multiple components. This is a very uninteresting link. Does anyone know what this is? Hop link. So we could do this again with a very slightly more complicated braid. You don't know what this is?
Excellent.
Trefoil line. And maybe in a few minutes, I'll just tell you what we try to do, like one approach to trying to differentiate knots, right? So in a similar way that I had a problem where I'm trying to tell whether these two things are the same thing, right? Whether these two words represent the same group element, or whether two braids represent the same group element. Over here we have a problem of trying to figure out whether two presentations of knots, right? A presentation is some way of writing down a knot that's like reproducible and other people understand. Do they represent the same knot? Are they the unknot in particular? Or could I tell, is there some machine that I can feed this into and it will just tell me whether that's the trephine knot or not? So there's this whole realm of knot invariance. Which are kind of meant to be machines that you plug knots into and they give you something, but that something should only depend on the kind of knot they are. So there's a kind of machine called the Jones polynomial, and when you give it the unknot, it gives you back some polynomial. Technically it has inverses too, but it's basically a polynomial. So if you apply this machine to something which is just, the unknot in disguise, it gives you back the same thing, so that's great. And when you apply this machine to the trefoil knot, oh dear, you get something else. I think you get like a v cubed plus b to the 5 or something, I don't know. But the point is you get something else. And so the Jones polynomial gives you like a kind of recipe of putting something in. You know that the unknot is this, and you know this one is this, and therefore this is not the unknot. And so it gives you like a machine for differentiating these things. And kind of where Braid groups, knot theory and representation theory collide is in the sort of production of new knot invariants. So how do you come up with something like this? How to make a knot invariant. So first you start off with some representation of a braid group. So a representation is basically a way of associating a matrix to each braid so that braids multiply like matrices multiply. So an example of a representation for the symmetric group would be permutation matrices. Right, so I could take this permutation and I could write down a permutation matrix. 2 goes to 3, 3 goes to 2, 4 goes to 1. Oh. Have I written this wrong?
Yeah, there's 2 ones. Sorry, bijective.
Let's do that then. Right, so this is a way of starting with a permutation and making a matrix, satisfying this rule. And in a nutshell, this is what representation theory is. Trying to come up with these things, trying to study these things, trying to figure them out. So what you do then is you start with your knot, you represent it as the closure of some braid, and then what you do is you put your braid through this machine and take the determinant or the trace or something of this matrix. Right, and this is in fact how this is one way of looking at the Jones polynomial. So there's an interesting representation of the braid group. It gives you matrices over polynomials rather than numbers, but you can then, take a knot written like this and evaluate the Jones polynomial by doing this. This is not actually how people calculate the Jones polynomial. There are simpler ways to do it. But if you ask, like, where the heck does this Jones polynomial come from? I want to find more things like it. You might go and try to do this setup. Experiment around and, find new braid group representations with the hopes of getting better and better knot invariants. Right, so I think I'll stop there and take any questions if anyone's interested.